the scalar product, or the dot product, or the inner product. I refer to it most often as the dot product. And here's the definition. So the dot product is when you draw a dot between two vectors to show multiplication. And in vectors, you'll find out later when we do the cross product that the different multiplication sign between vectors means different things. So the dot product, and the reason it's sometimes called a scalar product, is because the result is just a number. It's not a vector. It is a scalar. What you do is you multiply corresponding components and add them together. Kind of sounds like matrix multiplication, where you multiply things and add them together. So it's similar to that, but a little bit different. Whoa. Here we go. I don't know what that was. That was from last year, some important form. Oh, it was a game that we played. Anyways. Find the scalar product of these two vectors. So our first vector, v, so if you wanted to do v dot w, v is 2, negative 3. W is 1, 2. Multiply the corresponding components and add them. Not too bad.
Wait.
You will when we get to the angle, yes. When we get to the interesting things that happen with the dot product. So here we have one vector. Again, I really like writing them as column vectors. Dot product with 4, 1, negative 7. Multiply the corresponding components and add them together. No problem. And with everything what this is leading towards, because you could make up rules for things, but there's got to be a purpose. Where are we going with this? Why is this important? And what can we do with it? Well, here are some properties that result from the scalar product. And the vectors, they do act very much like numbers, unlike matrices. Here, the dot product in one direction is the same as the dot product in the other direction, which, if you think what's happening, makes sense, because you're multiplying corresponding components, and you know that multiplication doesn't matter the order, so the dot product doesn't matter the order as well. If you have a scalar multiple out in front, you could do the dot product first and then multiply by c. Or you could multiply by c by one of the vectors first and then do the dot product, or c by the other vector first and then do the dot product. With the dot product, you can distribute. So you could do the dot product of one and the dot product of the other and then add the results, or you could have added those two vectors to begin with and then do the dot product. And if you have the 0 vector, notice this 0 is bolded and this 0 is not. This one is a vector, this is a scalar. So if you multiply by the 0 vector, well, every component will get multiplied by 0. And you add all those zeros together, you will get 0.
You have to bold the 0 in the test.
No, you would have to do this. Draw it as a vector. Yeah, you don't have to, right? And then I determined, no, it wasn't bold enough. Now we get to the interesting stuff that happens. If you dot product the same vector, the result is the length of that vector squared. Okay? So let's take 3, 4, and the reason I chose 3, 4 is it makes a 3, 4, 5 triangle, right? If you dot product it with the same one, can you see that you're doing a squared plus b squared, which will give you c squared, which is the length squared.
Wow, it comes back again. Never rid of it.
And the most important result is the dot product is the length of one vector times the length of another vector times cos of theta, where theta is the angle between those two vectors.
To the x-axis.
So if I have the vector u here and the vector v here, and so those vectors are joined tail to tail, there is only one angle between those two vectors. That would be the angle theta. So if you take the length of u, the length of v, and multiply it by cos theta, the angle in between, you get the dot product.
Only the normal angle.
Is there a reason?
We'll look at some examples. No, it's just random. They just thought, oh, let's just random do this. Introduce another new word. A new word for perpendicular.
Seriously?
Yes.
Can they not stick with the word perpendicular?
If you weren't feeling like perpendicular was abstract and weird enough, right? Because it's used every day in life, right? I just came to that perpendicular street corner again, and right, because just not so you don't confuse it with other areas, we have another word, orthogonal. 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 I think that's how I pronounce it more often. Orthogonal.
Right.
Yeah.
Like a muscle or something.
Remember Miss Lefrance asked if anyone had that, but he was like orthodontist.
Orthodontist. Okay. So if two vectors are perpendicular, then the dot product is 0. So it becomes a very quick way for us to find out if two vectors are perpendicular to each other. And when the angle between two vectors is acute, in other words, between 0 and 90 degrees, well, we know that cos in quadrant 1 is positive. So as soon as our dot product is positive, we know the angles between 0 and 90 degrees. And if our dot product is negative, that would mean that the angle is in quadrant 2, and then you know that your angle is bigger than 90 degrees.
Bigger than 180.
Well, as soon as you get bigger than 180, if you say
Just making sure.
210 degrees, well, that's really
Got it.
the same as that angle there. Right? Because going past 180, if you're saying this is the angle, well, it's really the same as the smaller angle. So between two vectors, you can always think of the angle between them somewhere between 0 and 180.
Yeah.
Because as soon as it goes beyond, well, now they're closer in the other direction.
There's always a closer side.
And when two vectors are parallel, the angle between them is 0 degrees. And since we know that cos of 0 degrees is equal to 1, then the dot product is just equal to the lengths of both of those vectors. If you rearrange the formula that the dot product is equal to the length of u times the length of v cos of theta, you get a formula for cos of theta. And this can find the angle between two vectors really easily. The nice thing about this is this doesn't just extend to 2 dimensions, because you could find angles between things in the past in 2 dimensions, but now we can extend this to 3 dimensions,
Okay, so we know that cos theta is adjacent over hypotenuse.
right?
So would that mean the vector even b is the adjacent length?
No, it does not have to be that, right? Because I could have, well,
Because you said that.
should we just make up an example in 2 dimensions?
300.
Okay, so we can visualize it. Okay, wow, that's still very, very green.
Beautiful.
I'm going to take here we go. Let's take this point 1, comma 3. So this vector here would be 1, 3. And to make it nice and simple, we'll make this other vector at 2, 0. So this, as a vector, would be 2, 0. You want to find this angle in between. Now let's recap how you would do this using the mathematics you've learned in high school. Okay? If you wanted to do that, could you use the sine law? Sine law, you need an angle and an opposite side. So you don't have, I mean, you could figure out, it makes a triangle, right? You could figure out that side. I know that this length is 2 because I chose such an easy value to do it. I know that this length is 1 squared plus 3 squared, or the square root of 10. So based on what I have here, I would use the cos law. Okay, because I could also find this other side, right? Because I know that this is over 1, up 4, up 3 as well. Oh, it makes a nice isosceles triangle. Okay? So having all 3 sides, you would solve this with the cos law. A squared equals, well, it's usually, well, it doesn't matter the letters. B squared plus C squared minus 2 BC cos. The cosine law, not to be confused with the cafeteria and food services.
That's much tastier.
And you would plug everything in and solve this for theta. Okay? What we're doing now, so let's put these values in just to compare what's happening. So my a squared would be 10. The b and the c are your 2 sides that are adjacent to the angle, and it doesn't matter which one's which. So you would have 10 plus 4 minus 2 times root 10 times 2 cos a. So to get cos a by itself, we would have 10 plus 4 minus 10 all over negative 2 root 2 times 2. And sometimes you also have formulas. You might have had a formula in grade 11 where the cos A was already solved for. Normally this negative doesn't appear on the bottom because they factor it out.
Wait, what? Wouldn't it be?
Oh, it'd be the other way around. Thank you. Yeah. And you would get your ratio for cosine. In this case, it's going to be negative 4 over negative 2, negative 4 root 10. I'm going to leave it like that right now because you can obviously simplify that further and see it's 1 over root 10. But now let's look at what the dot product produces for us. When I do the dot product of these 2 vectors, I'm just going to get 2. Okay? The length of u times the length root 10 and 2. I mean, it also simplifies to 1 over root 10. Okay? Some of the things I wanted to show in this is that no, it doesn't necessarily match up perfectly.
Oh, it's because it's not a right angle.
It's not a right angled triangle. I also wanted to show in this that they both simplify to the same thing, but they don't simplify right away to the same thing. Like nowhere does this ever get a 2 on the top, and that's where we start with our 2 on the top there. But it gives us the same result. Okay. So let's go to 3 dimensions, because we can't draw this nicely in 3 dimensions. What you would have to do, I'm trying to think, if you're doing this analytically, and I have 2 vectors in 3 dimensions, okay? Anytime there's 2 vectors that are tail to tail in 3 dimensions, there would exist a plane. And when we talk about mathematically, when we talk about a plane, it's like a piece of paper that's a two-dimensional piece of paper that expands in all directions. So your two three-dimensional vectors exist in a two-dimensional plane. And you could then transport them to a two-dimensional kind of thing and then try to do the mathematics with the angle between them based on that. But even thinking about trying to do all of that becomes overwhelming.
That can't be perfect, can it? Because you can't convert a 3D object into a 2D object without losing some qualities. Just like you can't put a...
Well, you just are looking at this in, like, if they go in this direction, now I'm looking in this plane. If they're going like this, I'm looking at straight up and down. So cos of theta will be the dot product between these two vectors over the length of v times the length of w. Sometimes I make the dot product a bigger dot. Might. Because this dot on the bottom is regular multiplication, and this dot on the top is dot product of vectors. So cos theta is going to equal, well, if I think of this vector as 3, 2, 1, and this vector as 4, negative 1, 2, I'm going to get 12 minus 2 plus 2 is going to be 12. The length of v, a squared plus b squared plus c squared, square root of 14, and the length of w, 16 plus 1 plus 4, square root of 21. We can now find theta by doing cos inverse of the square root of cos inverse of 12 over the square root of 14 times 21. If you have your calculator set in radians, if you have your calculator set in degrees, and we're probably still more familiar with degrees. So 45.6 degrees. No. I think for the most part, I think we're more comfortable with degrees still. We'll do a lot of our answers in degrees, but it really does. No, there's no symbol for radians. You can write radians. There's been people who have advocated for like something like that, or a degrees registered trademark.
But like if you put an angle in degrees without the degrees,
Then it means radians.
you lose marks.
Yes.
Even if you meant degrees.
Even if you meant degrees, right? Because I'm sure you meant to get every question right on your test. But even if you didn't, should you still get the marks?
Yes.
I meant to get that one right. Yeah. That would be a nice ideal world.
Do that. You can do that.
It's like getting 4 attempts on every multiple choice question.
How about 5, just to make sure?
Just to make sure.
You know, sometimes people set the same question twice. Like, hey, you didn't get that right. A, I like it. B.
And that's unfortunate.
Some people are so...
In this question, you need the two vectors to be orthogonal. So what do we know about
Orthodontist?
about if they're going to be perpendicular and the dot product's going to equal 0. So if we take our first vector, 2m, m, and 8, dot product, bigger dot, with 1, 3m, and negative 1, we need this to equal 0. Multiplying this out, this will be 2m plus 3m squared minus 8 equals 0. It's a quadratic equation. I'll rewrite it. Hopefully we can factor this. If not, we'll have to use a quadratic formula, but checking the only way we could factor it is if it would be a 3m and an m. Is there a way to get 8, 2, and 4, so the outside 6 and the inside 4 make 2? I need to make the outside plus 6, the inside minus 4. You're going quadratic formula? This is so much faster. Oh.
I can't do it like looking at it like that, but I can take the steps in between and get that up to quadratic. What do I do with the quadratic?
Like, at best,
Ever since Mr. Jarrett showed that when we were in like grade 11 or 10, that's all I do. I put like the 3 in the M because I know it has to be. There's no way it's going to be 8 and 1. I'm just not going to work with 3. So I pick 4 and 2 and I just look at the signs.
at best, I'll do grouping.
I learned some cross stuff and it works really well.
Yeah.
It's wild. It's wild. But it takes a little longer.
Even if it's
Definitely can't do it like that.
Or you can every time get the right answer by doing the quadratic.
There you go.
You can waste your
you
test.
can waste your time.
Yeah. See you like
Why
tomorrow.
not just do like the product of something? I think of that.
Yeah. Mr. Jared's gonna have to get Eric to pick up Carson every single day.
Given the vector 4, negative 3, give a vector that's parallel to you. So here, yeah, you have to give a vector that's parallel, so that it means it has to be in the same direction as 4, negative 3. And any multiple in front will do that. So I can pick any value for k. If I choose k as 2, 8, negative 6. I would not use any properties of, I would not use the property of a dot product here at all to figure this out, because in order for them to be parallel, one just has to be a scalar multiple of the other.
It can't be the exact same as
It could, give a vector that is parallel to you.
That is not you.
Yeah, you're not picking you again. It's still right.
Yes, it is parallel, but
So why would you multiplying by 0 then make me the vector of 0? You guys are talking about same vector.
Well, sorry, what was that?
Would multiplying by 0 since that's mean that any vector is parallel to it?
No, it has to be a scalar non-zero.
Okay, that'd be cool. Because then you can just use multiply by 0 and you always get a parallel.
So if you want something not parallel to you, okay, you can just change one of the values, because that would show that they're not scalar multiples of each other. We're going to use this idea of a scalar multiple of another vector to show that it's parallel. Yes.
Just to be clear, if I was to put k as 1,
Mm-hmm.
it doesn't work if it's like it is parallel. Would you?
I think the purpose is to not make it the same thing. You're supposed to understand the concept.
He knew that.
Well,
I
I guess you do understand it.
I won't, but then I'll go through the rest of your test and find places that I normally wouldn't take off a half a mark and take them off, so it looks like I'm not taking it off for that one part, but I am. Yeah, like keepers. Yeah. And now I have to do that for you, Ramsey, because I put it on video. So you're guaranteed to lose a mark. Now in part C, for finding something orthogonal, here is where we will think and use the dot product. We need something here so that it's equal to 0. And you definitely can just flip them.
That's awesome.
Okay? Because if you think about a vector is really run over rise. Okay? Does that make sense? That a vector is run over rise instead of rise over run, but it's very much like a slope. So when you learned about slopes, perpendicular slopes, you learned about negative reciprocals. And now we're doing orthogonal vectors. You learned negative reciprocals.
Supposedly.
A half-mark deduction. Anyways.
They give him his own mic, so make sure you spell it like that.
Now, so 3, 4 is going to work. And if you look at it, sure enough, it's 12 plus a negative 12. You're going to get 0.
Negative 2.
Why would it be negative 3 then?
No,
Then it wouldn't make it 0.
Always opposite.
you flip it and you want
Okay? Now, when you did a negative reciprocal, you flipped the entire fraction, made the entire fraction negative. Here, it's not going to matter where you change it. So, for example, if you wanted to find something orthogonal to 2, 3, right? It could be 3 in the negative 2, or I could have negative 3 in the 2. It doesn't matter where that negative is. But as long as when you do the dot product, it's going to be equal to 0.
Put a negative outside. Does that multiply each group?
It would multiply each one by the negative. So you can't put the negative outside. Two vectors are defined as v and w. We want to find the value of x if they're parallel. So given that they're parallel, you know that they're scalar multiples of each other. What does that mean? That means that 2x and 1, negative 3 are scalar multiples. I can put a k in front of here or a k in front of there and solve for that k. It doesn't matter where. I usually go where I can visually see that k is going to be a nice number, or not a fraction. If I put it here, it's 2, right? If I put it here, it's a half. So I'm going to put it here, and then this tells me from my first set of components that 2 is equal to k. From my second set of components, that x is equal to negative 3k. And obviously, k is 2, because that's what this says. Plug in 2, and we'll get that x has to be negative 6 for these to be parallel. Same kind of idea that if you're going 1 to the right, 3 down, 2 to the right, you'd have to go 6 down. It's the same idea as a scalar multiple, but this really is, I think, the easiest way to go about it, especially if the numbers turn out not to be nice to work with. Perpendicular, well, that means that the dot product is going to equal 0. So we've got 2 plus a negative 3x equals 0. And x is equal to 2/3.
cross product. Yay. Wait, there's a
No.
right-hand rule?
I saw the paper, the guy had his hand out like this, and I'm like, why is he doing that?
What is it?
That's my hand.
What is it? Kinetic field?